Alright guys, so if you're watching these videos sort of as a sequence, which is sort of what I had hoped, we had started talking about quadratics with complex solutions, then we dove a little bit further into imaginary numbers, so a new number system for us. And now we'll talk a little bit about complex numbers, so sort of referencing back to that first video, quadratics with complex solutions. So here we have complex numbers. So complex number is any number that can be written in the form of a plus bi, where a and b are real numbers. So the real number a is the real part because that's sort of the standalone part. And the real number b is the coefficient to the imaginary value I. So a here is my real part and bi. So I is my imaginary part, but bi sort of makes up the imaginary part of this complex number. So we'll do a few examples with these, and then we'll talk about, in the end of the video, some operations, so adding, subtracting, multiplying, and dividing with complex numbers. So let's just sort of bring this back to the first video from this lesson, quadratics with complex solutions. So here I have two quadratics. It says find the roots and describe them. So for this first quadratic, I have x squared plus 2x minus 8, and we'll set them equal to 0 because it's asking me to find the roots. And it's not giving me a specific method, so I'm going to go ahead and complete the square here. So I would have x plus 1 squared. I know that this is really like x squared plus 2x plus 1. So right now these guys are matching up until this point. So what do I have to do to this one piece right here in order to get to negative 8? I have to subtract 9, so equal to 0. So there I just completed the square. Now I can add 9 to both sides, and I have x plus 1 squared is equal to 9. I can take the square root of both sides, so x plus 1 is equal to, and getting all sideways, x plus 1 is equal to 3, and I also know that x plus 1 is equal to negative 3. So here I have x is equal to 2. I can subtract 1 from both sides, and I can subtract 1 from both sides over here, and I get that x is equal to negative 4. So I found the roots, which is great, so I did that for the first one, and describe them. This quadratic has two real roots. X equals 2 and x equals 4 are negative 4 are very much so real numbers. So it has two real solutions. So two real solutions. Awesome. Let's move on to this one. If you have decided to print out these slides, I just ask that you change this to a positive 7 for purposes of moving forward with this lesson. That's a little typo on my part. So find the roots and describe them. Again, I'm going to set this equal to 0 because I'm trying to find the roots, or the x-intercepts, or the zeros. And I'll go ahead and I'll complete the square again. So I have x plus 1. And I know that this is really like x squared plus 2x plus 1. So what do I have to do to get from 1 to positive 7? And looking here, I would have to add 6. So what do I do to get from 1 to 7? I could add 6. So now I can go ahead and solve this. So I'll subtract 6 from both sides. So nope, we're not talking about x squared. So I have x plus 1 squared is equal to negative 6. Take the square root of both sides, and we can already see sort of what's happening here. I can see that I'm taking the square root of this negative number. So I have x plus 1 is equal to the square root of negative 6. And x plus 1 is equal to negative square root of negative 6. So here I am going to call this, let's get rid of this bottom one, or actually, you know what, let's move it over to the side. So x plus 1 is equal to negative square root of negative 6. So I know that this square root of negative 6 is really like the square root of 6 times negative 1. So I am going to call this x plus 1 is equal to I times the square root of 6. and I can subtract 1 from both sides and get that x is equal to I times the square root of 6 minus 1. So here's my first complex root or imaginary root to this equation, to this quadratic function. And my next one, again, I can do the same thing. So x plus 1 equals negative I square root of 6, subtract 1 from both sides. So x is equal to negative I square roots of 6 minus 1. And for writing this as we is sort of in the form a plus bi that we had talked about up above, so I'll go ahead and put a box around this one too. So we would say that x is equal to negative 1 plus negative I square roots of 6, and x is equal to negative 1 plus I square roots of 6, which brings us to sort of the next piece of these complex numbers. So here I have these two complex roots for this quadratic equation. So when we look at these two complex roots, I can see that they're really similar, except here I have a negative and here I have a positive. So when we talk about complex roots or complex numbers, conjugate roots. So irrational roots always occur as a conjugate pair. So we have this plus piece that we just saw up above, and we also have this minus piece. So they always occur as a pair. So the positive pair and the minus pair. And where that comes from is when I take the square root, just like over here, I have 3 and negative 3. Right, when I take the square root of 9 here, I have the positive piece and the negative piece. So that's just sort of, we're still following the same rules of a square root as we were before, but now we're sort of talking about it as a complex or imaginary number. So some examples: if 2 plus the square root of 3 is a root, so is 2 minus the square root of 3. If negative 1 plus the square root of 2 is a root, so is negative 1 minus the square root of 2. If negative 3 minus the square root of 8, we can also say negative 3 plus the square root of 8. And if the square root of 5 is a root, so is negative square roots of 5. So again, square roots always have the positive and the negative piece to them. So this is just going back to I. So sort of, why is I helpful? So I is helpful because it allows us to simplify sort of out of these square roots. So let's do a few examples and maybe we'll see what that looks like. So express the following in terms of I, the square root of negative 36. This is going to be 6I. The square root of negative 3, this is going to be I square roots of 3. Express the following in terms of I. This will turn into 1/8 I 8, or this is really over 1. So 8I over 8, which is just going to give me I. So we just simplified sort of this, for lack of a better term, complex sort of equation here, just down into I, which is a little bit nicer to look at and sort of a little bit nicer to work with. So looking at the square root of 20, I know that this is really like negative 1 times 4 times 5, or the square root of negative 1 times the square root of 4 times 5. So here, this piece is I, this piece is 2, and I still have the square root of 5. So this simplifies down to 2I square roots of 5, which again, a little bit nicer to work with. Looking over here, this is really like the square root of negative 1 times the square root of 1/2. I already getting a little bit ahead of myself there. Times the square root of 1/4. This piece is I times 1/2. So this is like I over 2. Over here, 2/3 square root of negative 72. I know that this is really like 2/3 times the square root of negative 1 times, let's, instead of 9 times 8, let's go with 36 times 2. So 2/3 I 6 times the square root of 2. So let's go ahead and write that a little bit nicer. This becomes 6I times 2 over 3 square roots of 2, not 3. So this turns into 12I over 3 square roots of 2, which becomes 4I square roots of 2. So again, just a little bit nicer to work with. Here, let's simplify before completing this operation. So we can add, subtract, multiply, and divide with complex and imaginary numbers. So looking here, the square root of negative 27 plus the square root of negative 48, these are pretty, they're just not super helpful to sort of do any kind of operation with them. Number one, we have some imaginary numbers. Number two, we can't combine these two pieces right now because they're different radicals and we're talking about addition. So here, I know that I can, I guess we'll go through some of this work. This square root of negative 27 is really like the square root of negative 1 times 9 times 3, plus this square root of 48 is really like negative 1 times 16 times 3. So the square root of negative 1 gives me I, the square root of 9 gives me 3, and I'm left with the square root of 3, plus the square root of negative 1 is I, the square root of 16 is 4, and I'm left with this square root of 3. So I end up getting this 3I square roots of 3 plus 4I square roots of 3, which is what I simplified this to down here. So I have an I and square roots of 3 here, so we can actually go ahead and simplify this into 7I square roots of 3. So by adding 3I and 4I, I'll get 7I square roots of 3. So I started with this sort of not so nice looking piece up here and simplified it into a single term, which was really nice. So going back to this, we can do some addition, subtraction, multiplication, and division with complex numbers, and you treat the I as if it's a like term. So addition with complex numbers, this would be 1 plus 5I plus 2 minus 4I. So 1 plus 2, that gives me 3, and 5I minus 4I, that's going to give me plus I, or 1I. So here we can add, subtract, multiply, and divide. So subtraction, we'll distribute this negative. 1 plus 5I minus 2 plus 4I. 1 minus 2 gives me negative 1 plus 9I. So subtraction with complex numbers. We can multiply with complex numbers, and so our same rules of multiplying variables applies here. So 5I times negative 3I, this is going to give me negative 15, and I times I is I squared. And what do we know about I squared? Is that it actually simplifies to negative 1. So this simplifies to positive 15, which is pretty cool. So going back to I squared, this is really like negative square root of 1, square root of negative 1 times square root of negative 1, which is going to simplify to negative 1. So this is multiplication with complex numbers and imaginary numbers is actually really cool. So this piece simplifies just down to 15, which is neat. So then we can also go ahead and distribute or FOIL, if that's what you like to call it. So 1 times 2 is 2 minus 4I plus 10I. And here I'll get minus 20I squared. So 2 negative 4I plus 10I is going to give me plus 6I. This is going to be minus 20, and that I squared turns into negative 1. So 2 plus 6I, this turns into plus 20. So 22 plus 6I. So again, this is sort of two complex numbers multiplied together that eventually turns into one complex number, which is really nice. It just makes it look a little nicer. Operations with complex numbers, so division. So this one is a little different, and if we think about what we're really doing here is this, remembering that I is the square root of negative 1, and how do we rationalize denominators when we're talking about radicals. So we're sort of doing the same thing here. I am going to multiply this by a fancy version of 1, and I'll pick a very specific fancy version of 1, and it will be the conjugate of my denominator. So 3 minus 2i. So here I can go ahead and distribute or FOIL these out. So it gets a little tedious here. So 3 times 3 is 9. This is going to give me negative 6i minus 12i plus 8i squared, all over 3 times 3 is 9 minus 6i plus 6i minus 4i squared. So we can see what ends up happening in the denominator here is my middle terms will simplify out with each other, and I'll go ahead and just move forward with simplifying this problem. So I'll get 9, negative 6 minus 12, that's going to give me negative 18i plus 8 times negative 1, all over 9 minus 4 times negative 1. So here, this will turn into 9 minus 8, so I'll have 1 minus 18i, and this turns into some addition here, because negative 4 times negative 1 will give me positive 4, so 9 plus 4 here will give me all over 13. So here, when I divide with complex numbers, we're just multiplying by its conjugate. So we can do one more example here. We'll go ahead and multiply by this fancy version of 1, which becomes 3 plus 2i, so 3 plus 2i. And so I'll end up getting 3 times 3 is 9, plus 6i minus 6i minus 4i squared. And in my numerator, we'll have 3 plus 2i minus 3i minus 2i squared. And we can go ahead and just continue to simplify. So 3 minus I minus 2 times negative 1. And I'll see here that my middle terms and my denominator end up simplifying out. So I'll get 9 minus 4 times negative 1 over here. This becomes 3 minus I plus 2, because negative 2 times negative 1 will give me that positive. This becomes 9 plus 4. So this turns into 5 minus I all over 13. So just some division with complex numbers. So just to sort of recap here, we'll scroll back up a little bit. We talked about complex numbers, how they have a real part, they have their real piece, and they have their imaginary piece. We can use complex numbers to describe quadratics that don't have real roots. Every complex root that we end up finding also has a conjugate pair to it. So that's just sort of a nice or a fancier way of saying when I take the square root of a number, it has a positive and a negative solution to it. Why is I helpful? So we can simplify things nicely. We can combine things that we didn't think that we would be able to combine. Then we moved along and we did some addition, some subtraction, so addition with complex numbers, subtraction, multiplication, and we did 2 division examples. So there should be a homework that follows along with this, and we can talk further about this on Tuesday or Thursday when we